By the end of this video, you will be equipped to confidently answer the question, explain how backpropagation works in your AI interview. We are going to explore a two hidden layer neural network with two inputs and two outputs. The goal of backpropagation here is to adjust the weights in such a way that the network's predictions become more accurate over time. In other words, the network learns. We have created an interactive online explainer that you can follow along with this video. Do try it out. First, we will talk about the forward pass. This is where the network takes the input data, processes it using the initial weights, and gives an output. This output is the network's first guess based on the input. Next, we will look at the cost function. This is a way to measure how far off the network's guess is from the actual answer. The goal of the network is to make this cost as small as possible. Then we will move on to backpropagation. This is where the network figures out how much each node contributed to the error. It does this by calculating deltas or errors for each node. Let's talk about the cost function, a crucial component in training a neural network. The cost function quantifies how far off the network's predictions are from the actual target values. The goal of training is to adjust the weights and biases to minimize this cost. In our network, we are using the mean squared error MSE as our cost function. The MSE measures the average square difference between the network's predictions and the target outputs. Let's calculate the cost for a simple example from our XOR dataset. Suppose we feed the input 1, 1 into our network and the target output is 1, 0. After the forward pass, let's say our network predicts 0.56 for the first output node and 0.62 for the second output node. We can calculate the cost as follows. Cost is equal to half of 1 minus 0.56 squared plus 0 minus 0.62 squared. This cost represents how far off our network's predictions are from the target outputs. During training, we will use backpropagation to adjust the weights and biases in a way that minimizes this cost. Let's talk about targets in our exclusive OR network. In machine learning, we often need to convert categorical data into a format that can be easily processed by our algorithms. This is where one-hot encoding comes in. Imagine you are trying to predict the weather and the possibilities are sunny, cloudy, and rainy. Instead of representing these as 1, 2, 3, which could imply some sort of order or magnitude, we use one-hot encoding. Sunny might be 1, 0, 0. Cloudy could be an array of 0, 1, 0. Rainy could be array of 0, 0, 1. Each category is equally distant from each other and there is no ambiguity. In our XOR network, our outputs are 0 and 1. We could represent 0 as an array 1, 0 and 1 as an array 0, 1. Each output node in the network corresponds to one possible XOR result. This clear, unambiguous signal helps our network learn more efficiently. So, for our XOR operation, if the target output is 0, we represent it as array 1, 0. If it is 1, we represent it as array 0, 1. That's the power of one-hot encoding. Let's dive into backpropagation, starting with our output node Z5. We are going to calculate an error term which we will call delta 5. This term tells us how a tiny tweak in Z5's total weighted input affects our total cost. Here's how we calculate delta 5. Delta 5 equals the change in cost with respect to A5 times the change in A5 with respect to Z5. The first part, change in cost with respect to A5 is simply the difference between our target output and the actual output from the network for node Z5. The second part, change in A5 with respect to Z5, is the derivative of the activation function at Z5. Since we are using sigmoid function, this is just A5 times 1 minus A5. So delta 5 becomes delta 5 is equal to difference between target 5 minus A5 times A5 times 1 minus A5. This gives us a measure of how much Z5 contributes to the total overall cost. Similarly, let's calculate the error term for node Z6, which we will denote as delta 6. This error term represents how much a small change in the total input at node Z6 will affect the cost. We express delta 6 as follows. Delta 6 is equal to change in cost with respect to A6 times change in A6 with respect to Z6. The term change in cost with respect to A6 represents how much the cost changes with a small change in the activation at node Z6. It's calculated as target 6 minus A6, where target 6 is the target output for the node Z6 and A6 is the actual output from the network. The term change in A6 with respect to G6 represents how much the activation at node Z6 changes with a small change in the total weighted input at the same node. Since we are using sigmoid function, our activation function, this term is calculated as A6 times 1 minus A6. So we can calculate delta 6 as delta 6 is equal to difference between the target and A6 times 1 minus A6. This gives us the error term for node Z6, which quantifies how much a small change in the total weighted input at Z6 will change the cost. Let's grab a pen and paper and visualize the process. Draw an arrow from target 5 to node Z5 and another arrow from target 6 to node Z6. These arrows represent the change in cost with respect to the activations A5 and A6. Now inside the nodes Z5 and Z6, draw arrows from A5 to Z5 and A6 to Z6. These arrows represent the change in activation A5 and A6 with respect to the total weighted inputs Z5 and Z6. Next, draw arrows from node Z5 to node Z4 and from node Z5 to node Z3. Do the same for node Z6. These arrows represent the weights connecting the nodes. Finally, inside node Z4, draw an arrow to A4 to Z4. This arrow represents the change in activation A4 with respect to the total weighted input Z4. Now, to calculate the change in cost with respect to Z4, you simply multiply the changes along each path and add them up if there are multiple paths leading to Z4. This is the essence of the chain rule in calculus, and it's the fundamental principle behind backpropagation in neural networks. Mark the changes along each path and use some notation like delta of cost with respect to delta of A6 to help you remember what each arrow represents. This diagram will be quite handy in future. Instead of recalculating the change in cost with respect to Z5 and Z6 for each node in the previous layer, we reuse the values we have already calculated. This is one of the efficiencies of backpropagation. By storing these errors or deltas, we can avoid redundant calculations and make the learning process more efficient. So the errors we called for nodes Z5 and Z6 are used again when we calculate the errors for nodes in the previous layer like Z4. Let's calculate the change in cost with respect to a small change in Z3. that we call delta 3 with a drawing exercise. Grab your pen and paper and draw an arrow back from target 5 to node 6 and from target 6 to node Z6. Draw another arrow inside node Z5 from A5 to Z5 and inside node Z6 from A6 to Z6. Now connect Z5 to Z3 and Z6 to Z3 with arrows. Draw an arrow inside the circle node for A3 to Z3. To calculate the change in cost with respect to Z3, you will multiply the changes along each path and sum them up if there are multiple paths to Z3. Mark the changes with small notation like delta cost, delta A5 for the path from target 5 to Z5 and so on. Remember, the errors we calculated for the nodes Z5 and Z6 are used again when we calculate the errors for nodes in the lower layers like Z3. This is a beauty of backpropagation. We reuse these errors to avoid redundant calculations and make the learning process more efficient. Let's focus on updating weight W3. To figure out how a change in W3 affects the cost, we need to consider the path from W3 to the cost. We have already calculated how a change in Z3 affects the cost. That's our delta 3. So we can reuse delta 3. Now we need to consider how a change in W3 affects Z3. If you recall, Z3 is calculated as W3 times the activation at node Z1. So a small change in W3 will result in a corresponding change in Z3 scaled by the activation at node Z1. The new W3 is the old W3 minus the product of the learning rate, delta 3, and the activation at node Z1. This updated W3 will be used in the next round of forward pass and backpropagation, helping the network's predictions get closer to the target. Thank you for joining me on this journey through the workings of a neural network. I hope you found it interesting. Keep exploring, keep learning, and I will see you in the next video.